Greetings and welcome to the Philosopher's Corner. I'm Professor Hanson and I hope you are all doing well. Today I would like to address a request made to me by Professor Anton, who asked me to watch a video entitled Logic for Kids from a channel entitled Logic Rolls the Dice to see what I thought about it. As it turns out, I thought that the author had a fairly decent understanding of the logical absolutes, as he called them himself. But because of his terminology, and I believe ultimately a misunderstanding of formal logic, he got himself involved in metaphysical issues in the sense that are, as far as I'm concerned, ultimately foreign to formal logic. In other words, when the author of Logic for Kids started out, he pointed out that he had a blank slate in front of him, and that was a good thing, and we could call that non-reality. And so on the slate he writes the symbol for not and the symbol for reality, a little r, basically using this to represent non-reality. And then, in order to distinguish this, he says we can, of course, think of reality, and he uses the symbol r. So he establishes a pair of opposites, and he points out, as a matter of fact, that there is no middle ground between these opposites. There he is basically establishing a two-valued system. But then he proceeds to talk, and even from the beginning, using the notion of reality, he's talking as if formal logic is addressing the existence or actual physical properties of objects, and I think that is due to a failure to distinguish between what I would call the two aspects of reality. As you see here, I have the material aspect of reality listed on the left-hand side and the formal aspect of reality on the right-hand side. And I think this distinction is necessary for logic because we have logics that address the material side of reality and a logic that addresses the formal side of reality. And I think in order to understand the formal logic, we need to keep it absolutely distinct, at least in the beginning, from material reality and material logic. So material reality, of course, is the type of reality we get, or the notion of reality we get through our senses, the perception of objects, as we say. Whereas the formal aspect of reality is related to the conception of ideas. Now here, the notion of conception is used in a very general sense, but basically what I'm saying is we can perceive, we can see, for instance, physical objects, or we can think of the relationships between those physical objects, and those are two different ways of looking at the world, two different aspects. The one I call the material aspect, and the other I call the formal aspect. The material aspects, then, to understand those, we used what we call material logics, the logics of the material world. Those are abduction, adduction, and induction. The first two are the logics of material causality. The third is the logic of material analogy. In contrast, the formal aspect of reality has only one logic that applies to it. We call that formal logic. It is known as deduction. And we use that to corroborate the ideas that we have discovered with the material logics. The material logics are said to deliver what we call logical contingency, which is to say that the inferences we use, or we draw, when we use the material logics, the truth or falsity of them is contingent upon the situation in the material world. We are describing the material world. And so the truth or falsity of our inferences will, of course, be dependent or contingent upon that. With respect to the formal logic, however, what we do is we say, if something is true, what else is necessarily true? Which we call, of course, logical necessity. And, of course, if our axioms are true, then our theorems will be true because we try to guarantee the logical necessity in formal logic. Excuse me. So once we have this distinction, we can see that we need to keep our formal logic, in a sense, clean of material components or implications. Right? But nevertheless, of course, we do need to start with some logical form. And the way the author of Logic for Kids starts out is certainly acceptable. He establishes a polarity between reality and non-reality. Now, again, I try to shy away from the terminology of reality or non-reality in formal logic. And of course, there is a basic opposition in formal logic that even our author um, utilizes, because ultimately he talks about truth and falsity. And so rather than thinking of reality and non-reality as the basic opposites, I would like to introduce the notions of true and false, what I call the two logical values. Um, and so basically, true here will be represented by an up arrow and false will be represented by a down arrow. This I do to avoid any implication of true and false. Basically, we just want to see these as forms, and as long as we have a pair of opposite symbols, that will represent the form of opposition that we are seeking. Again, this establishes a two-valued logic. That is not to say that that's the only kind of logic there is and that reality is a two-valued situation. I believe reality is an infinitely valued situation, and so the notion of three-valued logics, where we might have something like true, false, and indeterminate or intermediate, and an infinite valued logic where we have true being one, false being zero, and the possibility of statements taking a true or false value anywhere in between the 0 and 1 in terms of the fractional element. So a statement might be 66% true or something like that. That infinite valued logic, of course, is the logic of probabilities. So those are certainly useful notions, but here we will start with the simplest form and take a two-valued logic. In addition to the two logical values, I have, as you see here, the three logical operators. These are things that operate on the values, and the things that take the values we would then call operands. Ultimately, I will describe those. Here, however, I want to talk about the three operators of not, or, and negation, disjunction, and conjunction. Excuse me. In particular, for the not operator, of course, we can combine that with a true statement, and we can combine that with a false statement. And as we know, of course, a not true statement is false, and a not false statement is true. I'll talk about that in a minute. Uh, what most people are not aware of is that the situation with or and is similar as well, because as we will see, or and in their structure are also a pair of opposites, or like a pair of opposites. And as it turns out, every or statement can be written as a not and statement, and every and statement can be written as a not or statement. And so again, the one is convertible into the other by means of the operation of not. What this does is transform our simple duality, a form of opposition, into what you might call a polarity, or as I prefer, a syzygy, which involves a pair of opposites and opposition, but also a third item that allows the opposites to convert one into the other, or at least be intimately related. As I've said, not true is false, and not false is true, and clearly the not operator combines or ties the true and false duality together in a special way. But of course, we have the same thing with here, and whenever we have a duality combined by this third element, we can call that a syzygy. Right? So the structure we're investigating here is the syzygial structure of a pair of opposites united in a third. And so at this point, what we can do is proceed to give the rules for combining these symbols that allow us to create what we call propositions. Propositions are things that can be judged as true or false. For instance, in natural language, we make the distinction between interrogative sentences, which ask questions. We don't ask if those are true or false. Imperative propositions, which give commands. We don't ask if those are true or false. And declarative propositions, which make statements about the world. And of course, those are the ones that we ask, are they true or false? excuse me. So a proposition then is uh, anything that can be judged as true or false. Uh, So when we use the symbols here, basically we will replace true or false with proposition symbols because a proposition can be either true or false. But at this point, I will give you the rules for combining the symbols and the rules that for the meaning of the symbols in terms of the up and down arrows only. So beginning then with not, as you see here, here is a symbol. The colon says, of course, that this applies to not. Um, and so as we see, in terms of syntax, the rules for combining the symbols, we can combine the not symbol with the true, or we can combine the not symbol with the and. Those are valid propositions. In terms of their meaning or semantics, we see that, as we know, not true is the same as false. And at this point, since I have not introduced the symbol, I do not feel a need at this in this logic for beginners to um, follow the rules of logic strictly. I want to make it as easy as possible. We'll just use this symbol to mean is the same as in terms of logical value. And clearly, the logical value not true is the same as the logical value false, as we know. And of course, not false is the same as true. So here are the syntactics and the semantics for the not operator. For the or and and operators, I will give the syntax first, the syntactics, and then the semantics second. So for the operator, or, as you see, there are 4 combinations, and for and, there are 4 combinations as well. That is because, of course, there are 2 logical values, true and false, and with each of them, true, for instance, we have a possibility of 2 more, and false, we have a possibility of 2 more, and so there will be 4 combinations. So we have here true or true, true or false, false or true, false or false. For and, we have, of course, exactly the same thing because it requires 2 propositions as well. And there will be 4 combinations. So we have true and true, true and false, false and true, false and false. And these are all of the possible allowed combinations for or true and false and true and false. In terms of the semantics, as we will see directly, for or, as it turns out, these 3 statements are true because an or statement only needs one and can have both of its propositions true in order for it to be true. If an or statement contains 2 false propositions, that of course is a false statement. And for and, what we'll find is it's, in a sense, the opposite, as I said. For and, only the first combination will be true because, of course, an and statement requires 2 true components in the combination for it to be true. Otherwise, it will be false. So, turning then to the next slide, we see, excuse me, on the top, the semantics for or. That is to say, if we have true or true, that's the same as true or false. That's the same as false or true. And all of those are the same as true. In other words, these 3 are true propositions, and only false or false gives us a false proposition. Contrarily, for and, we find that only the combination of true and true gives us a true statement. Because, of course, if an and statement has one or both parts false, it will be false. So false and false is the same as false, and true is the same as true, and false is the same as false. These are all false, and these are all true. Right? And in addition, of course, the physical display given here illustrates the polarity, the duality, the opposition of and or, even in terms of symmetry. Whereas, of course, this combination right here is the mirror reflection of this combination right here. And this row is a mirror reflection of this row. In fact, the upper part of the diagram for or is a reflection of the lower part of the diagram for and we see the syzygial structure right there. Basically, these are 2 different things that have something in common. Their form, even though it's a sort of a form of opposition. At this point, we would typically talk about different combinations of and an or and not, and point out the fact that, as I've said before, every and statement can be written as a not or statement, or every or statement can be written as a not and statement. And then we would go on to introduce the notion of implication in terms of not or not and. In other words, we would use implication as an abbreviation for some not or not and statement. And then we would introduce the equivalent symbol that we've been using here as a combination of two implications. Rather than go through all of that for beginners, I will simply introduce the symbols and give you the rules of syntactics and semantics for both of those so that we can proceed. All right. Turning to that then, we see that for the symbol for implication or implies, we find that when a true implies a true, that's the same as when a false implies a true. It's the same as when a false implies a false, and all of those are true. Now, clearly, when a true implies a true, that is understandably true. But for the other two, we assume that a false statement implies anything, and so we allow those to be true as well. That leaves, of course, only one of the four possible combinations, as before, to be false. And so we say that if a true statement is said to imply a false statement, that is a false statement itself. Again, equivalence is a combination in the sense of two implications, but ultimately what it says is that what is on one side or the left-hand side of the symbol is of the same logical value as what's on the right-hand side. And of course, that is only the case if we have a true and a true or a false and a false. Clearly, those two are the same, and those two, and so the question, are these values the same? The answer is yes, those are true statements. If we have true and false or false and true, clearly those are not the same. And so the question that asks, are these of equivalent value? And of course, the answer is no, that is a false statement. Right? So there are our five logical operators: not, or, and, implies, and equivalence. And at this point, we can proceed to introduce another syzygial, another oppositional structure, although I won't explain this one because in order to understand this, we require the upper levels of mathematics known as algebraic structures. What we're actually talking about are groups here. Boolean algebra is a combination of a couple groups, which again adds another level of opposition and syzygiality to the form that we're investigating. But rather than go through the mathematics, I will just introduce the ideas. So as we see, what we're talking about here are the axioms of algebraic structures. These axioms are the rules that give us not only the logic that we're studying here, but if we use a slightly different collection, here we're using a collection of propositions that are true or false. If we use a collection of numbers, for instance, the real number line, and slightly different operators instead of or and, we use addition and multiplication, then we have another type of algebraic structure. In other words, arithmetic is a type of algebraic structure, as is Boolean algebra or propositional logic. And so I'm using here the rules of arithmetic, which I have to assume people are more familiar with, to illustrate the rules of logic. In arithmetic, as we know, in addition, there is a particular number such that if you add that number to any other number, it returns the value of the other number. The identity of the other number is preserved. Right? And similarly, for multiplication, if you multiply anything by 1, in other words, n times 1 is always n, so that using 1 in multiplication preserves the identity of the other element. Therefore, 0 and 1 are called identity elements, and they are identity elements for a specific operator. 0 is the identity element for addition. 1 is the identity element for multiplication. And if these operators do not have their identity elements, they do not function properly. That is why if you want to do arithmetic using only two numbers, you can't use 1 and 2 because then addition would not have its identity element. Now you could use 2 as if it were a 0, but that is the same thing as using 0, of course. So if you use 0 and 1 as the only two numbers, you can represent all the numbers with it, and you can do the operations of addition and multiplication as they are intended to be done. Similarly, for Boolean algebra or propositional logic, our operators need to have their identity elements. For the operator of OR, the identity element is a type of false, but this sub-zero is used to indicate that this is a statement that is not just merely false, but is false all the time. It's what we call a contradiction. Okay? And the identity element for AND is a statement that is similar to true, but this one is one that is true all the time. It is known as a tautology. So, as we see, if we OR any proposition whatsoever with a contradiction, then the value of the proposition is equivalent to the value of the single statement P. Here we have the equivalent symbol, and now we have an equal sign inside it to distinguish it from the previous type of equivalence, which can be true or false. Here, this equivalence here is always true. It can't possibly be false. And that is because, of course, with an OR, we only need one true statement to make it true. Since that's false, if that's true, this whole thing will be false, but also, since that's false, if that's false, the whole thing will be false. Again, I may have said that wrong. If this is true, then even with this false, we have a true statement, and so the value of the expression is the value of P, as we see here. And of course, if this is false, we have two false statements, which makes the whole thing false. And so ultimately, the value of the whole expression is a value equal to the value of the single variable P, and that is basically using the identity element for OR. Similarly for AND, since we require two truths here in order to be true, and this is always true. If P is true, the whole expression will be true, and so the expression of the value of the whole expression is equal to the value of P. If P is false, of course, that will make the whole AND statement false, and so again, the value of the expression is the value of P. And so we see that without fail, necessarily, which is of course what the equal symbol stands for, the value of P or a contradiction is equivalent to P, and the value of P and a tautology is equivalent to P, as with the arithmetic identity elements. Moving on, the next thing we see are the axioms of opposites. As we know, again, from arithmetic, if we add opposite numbers, now here I should have a plus n and a minus n, but what I've done is just left the plus off of here and used our negative symbol for the propositions in order to have the form a little bit closer. But clearly, plus n plus minus n equals 0. And as it turns out, of course, 0 is the identity element for addition. So when you combine opposites in arithmetic with addition, you get the identity element for addition. For multiplication, if you combine opposites by multiplication, this would be, for instance, 3 over 1 times 1 over 3. That always, of course, equals to 1, which again is the identity element for multiplication. So when we combine opposite numbers with multiplication, we get the identity element for multiplication. Something similar occurs in logic, but it is slightly different, and that sets it off as a different tool, if you will, from arithmetic. Here, we can combine opposite statements. It is valid to say P or not P, basically. But as it turns out, this is equivalent to a tautology. In other words, this is always true, just as we have down here. And of course, a tautology being an identity element. When we combine opposite propositions with OR, we do get an identity element. And of course, when we combine opposite propositions with AND, that's also equivalent to an identity element. But here, for AND, we get the identity element for OR, and when we combine opposites with OR, we get the identity element for AND. That is different. It's a reverse from down here, and that marks an important difference between logic and arithmetic, or propositional logic and arithmetic. In addition, of course, we need to point out that this is just the law of excluded middles. A proposition is either true or it's not true, and that statement is always true. It's a tautology. Excuse me. And this, of course, is an example or is a representation of the law of no contradictions. To say that something is true and not true is a contradiction, and we're not allowed to do that. So we would say not P and not P. But now, of course, whereas the author of Logic for Kids is a little bothered by these ideas and talks about a little bit about that, we can avoid that because we are not concerned with physical reality. We are not saying that something has to be or not be, or it can't be and not be at the same time, because all we're talking about are logical values. And what this proposition says merely is that if we assign a logical value of true to P, the only other logical value there is false for P. And of course, that's a necessarily true statement. And of course, what this one basically is saying is you are not allowed to assign the two different logical values to the same proposition. You have to either call what true, I'm sorry, it's true, it can't be true and false at the same time. Right? And since this says nothing about physical reality, we do not have to worry about those issues of whether or not these are sometimes true and sometimes false. Here, basically what we're saying is we are going to assume these are true and see what kind of system we get from that. If we get a system that is applicable even to parts of the real world, the material world, then we have a useful tool. All right? And of course, nobody is bothered by the fact that when you combine opposites in addition, you get nothing. Now, granted, we were bothered by that for a long time because in the West we did not even have a symbol for nothing. It seemed to make no sense until it was brought in by the Muslims who got it from the Arabs, of course. Excuse me. Moving on then, what we'll find now are rules that are much more familiar from arithmetic than from logic, but nevertheless they hold in both cases. The first one is the axiom of commutation, which is in logic is similar to, for instance, 3 plus 3 equals 4 plus 3. We can switch the numbers around in addition and it doesn't make any difference to the answer to the question. Here also, P or Q is equivalent to Q or P, and the order of the statements in an or proposition is irrelevant. It doesn't make any difference to the truth. Similarly for and. P and Q is the same thing as Q and P. And so again, the order for conjunction is irrelevant. Next, we have, of course, the axioms of association. This is similar to, for instance, 3 plus 4 plus 5 equals 3 plus 4 plus 5. Here we have P or Q or R is equivalent to P or Q or R. Similarly, P and Q and R is equivalent to P and Q and R. Again, the grouping, the order here is irrelevant. And we are familiar with these rules from arithmetic, and so I don't think we need to dwell on them any further. What we're doing here is laying down a set of axioms. This happens to be the third and the fourth. And ultimately we'll have 5 axioms for algebraic structures. The fifth then is the axiom of distribution or distributivity. Right? And this one I do illustrate with arithmetic because, again, the situation in logic is different from the situation in arithmetic. In arithmetic, as we know, multiplication will distribute over addition, so that b times n plus m is equal to b times n plus b times m. However, addition does not distribute over multiplication. It is not true that, or in other words, b plus n times m is not equal to b plus n times b plus m. The second distribution rule does not exist in arithmetic, but it does in logic because we're dealing with slightly different objects, the propositions, as opposed to numbers, and slightly different operations. So we have P or Q and R is equivalent to P or Q and P or R, and then we have P and Q or R is equivalent to P and Q or P and R. And so here again we have 2 distribution rules that again gives us a different tool from logic. Now we have the structure that we need to work with. These 10 axioms, or 5 axioms, 2 for each of the 2 operators, gives us the structure of basically of a Boolean algebra, or having and or and not pretty much work the way we need them. Right? What we need now, in addition, are a few rules that allow us to, once we have created a line in a proof, let's say line 1, we'll assume something to be true. How do we get to line 2? Right? These rules here can be used for that because what this is saying is this expression here is the same as this expression here. And so if you need to get at this expression when all you have is this, you can, if you have a line in your proof like this, write it out like this and therefore get at that expression. But all of these, as we have seen, are two-way rules. We're talking about equivalences. We also need some one-way rules, and so now I would like to introduce them. So here are the rules of transformation, as we call them. The first rule is actually a traditional rule, a rule from classical logic known traditionally as modus ponens, the mode of putting. Um, Here it is called formal implication because what we do is we create a form of implication that cannot possibly be false. In other words, it is a tautology. And so to distinguish formal implication from material implication, we again put the equal sign inside the implication symbol. What this rule is saying here is if you have a material implication such that if P is true, then Q is true, and you also know that P is true, then you can deduce that Q is true because P gives you Q and you have P, so you are given Q. And that is always true. This cannot possibly be false. And so if we use this, in other words, if we have a line in a proof like this and a line in a proof like this, then we can create a line in a proof that looks like this, in other words, using this part right here. And if these are true, this will always be true. And that is that is all that is required from formal logic. In addition, we have two more rules that are connected to each other, basically allowing us to use the value or the power of the conjunction, the and statement. Right? Because basically an and statement requires two true components in order to be true. And so if we have a line, for instance, like P, and it's assumed to be true, so assume this is true and assume Q is true on a different line, you can create a new line that uses the conjunction of P and Q, and again, this will necessarily be true. In other words, this follows necessarily from this because each of these are true separately, and so they will be true in combination with and. Conversely, if we start with an and line, if we have a line that has an and statement, we can, in a sense, peel off either side because if the and statement is true, both sides will have to be true. And so if we have a line like this, we can create a line such as P from P and Q, and we can create a line such as Q from P and Q. Because we are starting with specific lines here, two specific lines that are true individually, and moving to a generality of saying both of those are true at the same time, I call this symbolic induction, moving from the specific to the general with symbols. And of course, conversely, because we start with the generality, P and Q here, and we move to specific lines, two different specific lines, I call this symbolic deduction. Right? These are the three rules that we will use to apply along with the axioms that we have introduced in order to do proofs. And so now we can proceed to that. Here we have an example of two different proofs, one on the top and one on the bottom. They happen to be Theorem 1 of the system that I have developed and Theorem 2. And these are traditional theorems in the study of logic. Theorem 1 is known as idempotency, which is the Latin phrase for its own power or power of itself. This is also known as tautology, as a matter of fact, which means basically that it is merely referring to itself. And as you see, of course, in the symbolic expression of it, this part of the whole proposition is referring to this other part of the proposition, and therefore it is tautologous. Right? What it says, of course, is that if you have a true or statement that combines R or R, then you can be absolutely certain that that is exactly the same as R itself. In other words, if R or R is true, then R is true. And of course, we can see that very plainly. Or only needs one true proposition in order to be true, right? But in any case, if R is true, just by itself, and of course that's what has to be true as well, but even if it were only true on one side, this would be a true statement, and of course R has been said to be true. That does not prove it, however. In order to prove it, what we need to do is to start with one side and then apply our axioms and our rules of transformation to produce the other side. If we can do that, then we're using, in the axiom, rules that talk about logical equivalence. So if one side is true, the other side, or in other words, if one line is true, the next line will be necessarily true, right? Or if we apply the rules of transformation that involve formal implication, then basically if the line we start with is true, then the line we produce with formal implication will be true. So what we will do here is start with the left-hand side of this proposition and apply our rules in order to see if we can produce the right-hand side. So for line 1, we just write down the left-hand side and we assume by hypothesis that this is true. If R or R is true, then from the rule for identities for and, which says that a proposition is the same logical value as that proposition anded with a tautology, we know that if R or R is true, then R or R and tautology will necessarily be true. For the next step, of course, this basically stands for any tautology whatsoever. We can replace that with a specific tautology, which is one of the any tautology whatsoever, and we will have an equivalent statement. This, of course, is following the rules of opposites for or. Opposites for or are the same thing as a tautology. And so line 3, by the opposition of, the rule of opposites for or is equivalent to line 2. Okay. Then, of course, here we have two or operators inside parentheses separated by an and since here we have R or and here we have R or, this looks a little bit like somebody has done a distribution, and so we can undistribute, if you will, pulling out the R or from both sides, setting it out here, and leaving R and not R, which is what we write down here. So by distribution, line 4 is equivalent to line 3. Next, of course, we notice that this particular expression here is a contradiction, R and not R, and basically we're combining opposites with and, which is always the same thing as the contradiction. And so we can replace this specific contradiction with a symbol for any contradiction whatsoever, and line 5 will be equivalent to line 4. Finally then, in a sense using a rule similar to this, but now identity for or, we know that f sub o is the identity element for or, and so R or f sub o, as a matter of fact, anything or f sub o is equal to that thing, so R or f sub o is equal to R, and so R is equivalent to I should say line 6 is equivalent to line 5, which is equivalent to line 4, equivalent to line 3, equivalent to line 2, and equivalent to line 1. So line 1 is equivalent to line 6, and line 6 is equivalent to line 1, which is what this says. Next, we will prove a little more interesting proof, perhaps. It happens to be the second one of the system I developed. Traditionally, it is known as addition. I prefer to call it disjunctive augmentation, but in order to get the words in here, I have just called it disjunctive addition. Basically, what it says is that if you have a true statement, then you can create an or true statement out of that true component, because, of course, or only needs one true component in order to be true. So if P is true, then necessarily P or Q is true. And I just realized now that this should not be an implication. I screwed up in this symbol here. I'll have to change that, because it is not true that P or Q necessarily implies the truth of P, because P or Q could be true when Q is true and P is false. And in that case, this equivalence I have here would be incorrect. And so this is not an appropriate representation. What I want is that P logically implies P or Q. That's because, of course, if P is true, then necessarily P or Q itself will be true. In order to prove this, again, we will assume one side, apply our axioms, and in this case, a rule of transformation in order to produce the other side. So starting then with line 1, assume P is true by hypothesis. By the rule of identity for or, this is the same as P or F sub O. Then, of course, by the rule of opposites for and, we can replace this any tautology, any contradiction whatsoever with a specific contradiction, and so line 3 will be equivalent to line 2. Then, of course, we can actually distribute here because we have or on the outside and on the inside, and or distributes over and so we get P or Q and P or not Q. And then, since we have a true statement here, a true and statement, um, if the and statement is true, both components must be true, and so by symbolic deduction, we can take one part of this and say that it is necessarily true as well. Therefore, the truth of P implies the truth of, the truth of 1 implies the truth of 2, implies the truth of 3, implies the truth of 4, implies the truth of 5. In other words, the truth of P implies the truth of P or Q, and the proof is finished. Next, I would like to prove one of the 3 laws of thought mentioned by the author of Logic for Kidz. I actually include a 4th law in the laws of thought, the law of double negation. But I think for the problems encountered by the language of author for Logic for Kidz, was most acute when he was talking about the law of identity. Because, again, he takes that to be talking about, in part, about physical objects and material objects. So, with respect to the law of identity, which often, of course, is cast in the terms of A is A, here, of course, we use our equivalent symbol and say that the value of P is equivalent to the value of P. Rather than saying that this also has material implications, we restrict it to the formal realm entirely. That's because, of course, with respect to material objects, it is not necessarily true to say that A is always A, or even A is A, in a sense, right now, because right now is just simply not precise enough, and if I say that something is A right now, in a fraction of a second, it has actually changed. So strictly speaking, it is no longer A. That is the problem with material objects. As a matter of fact, that is the reason that we revert to this type of stuff, because we want to remove the problems of material logic in the material worlds in order just to investigate the pure form without any contamination from the material ideas. Right? And so basically, rather than saying that A is A, and actually in order to make that statement correct, you would have to say A with a given index, a time index. This is pointed out by Alfred Korzybski, for instance, in his Science and Sanity, General Semantics, as it's known. Basically, if you want to exactly pinpoint a physical object, now it's even impossible to do it that way, but you can use an index, a timestamp, and so at time X, A is A. At time X plus some other time, X plus T, A will not necessarily be A, right? Because things change, right? But you can say with the stamp that A sub X is A sub X. In other words, the value of whatever A is at time X is the value of whatever A is at time X. But that is exactly what we are doing here. We are basically removing the time component entirely, focusing on form entirely, and of course the logical value. And here we're saying that whatever logical value P is assigned, that will be the same as the logical value of P. And of course, that is perfectly obvious. And with respect to logical values, when we assign a logical value to a proposition, it doesn't change unless, of course, we're done using that variable. We do not change horses in midstream and say that something we have called true here is false down here. That is not allowed. And so basically, the law of identity, strictly speaking, be called the principle of equivalence. Basically says that P has the same logical value as P. And of course is intuitively obvious. Here we actually have a proof for it. It's sort of a contrived proof, but it's meant only to illustrate the methods of formal logic. So again, we'll start with one side and see if we can produce the other side. Clearly, as soon as we start with one side, we've got the other side. But we can also do that by applying some of our rules, right? So the first thing we apply, first, of course, we assume that P is true by hypothesis. But if P is true, an OR statement containing P will be true, and we can actually OR it with anything we want. This is called, again, disjunctive addition or disjunctive augmentation. And so I have decided to OR P, which is true, with not P, because P being true makes this a true statement. So if P is true, P or not P will be true, right? By the rule of disjunctive addition. Then, by the rule of commutation for OR, I can reverse the order of these and have a proposition that is logically equivalent. Right? So 3 is logically equivalent to 2. Right? Then we fall back on the definition, the one I skipped earlier for implication. The definition of material implication says that what we mean by material implication in logic is the same thing we mean by not or. In other words, not P or P in logic is logically equivalent to P implies P. And so I can replace this line with this line by the rule of material implication. Combining then line 4, which is an implication, with line 1, which is the assertion of the truth of the antecedent of the implication. In other words, P implies P and P is true. This is an example of formal implication, the first of the transformation rules, right? And when we combine those two lines, line 1 as the implication, line 4 as the antecedent, then we can assert the truth of the consequent, which is P. Therefore, P is equivalent to P because, of course, all of these rules, uh, except for the last one, formal implication, which is used up here as well, are equivalent to, are rules of equivalence, right? And finally, I would like to prove a lemma. The official name I use for it is the perniciousness of inconsistency. Couldn't get that phrase in here, so I call this assuming a contradiction. It's a lemma to Theorem 2 in my system, I believe. It might be Theorem 3. But basically, it shows why we do not allow contradictions in formal logic. Right? As we see here, P and not P is a contradiction. We're not allowed to assert the truth and falsity of a statement at the same time. Right? And what we're going to see is that if we do allow that, then that implies the truth of any proposition whatsoever. That's what these variables stand for. This stands for any proposition whatsoever. This stands for the negation of this any proposition whatsoever. So if I stick one in there, I got to stick the same one in there and use the word not. But this is any proposition whatsoever. And so what this says is the truth of this statement implies any proposition whatsoever. That is always dangerous because, of course, not every proposition is true. We only want to imply the true propositions true. In other words, we don't want our logic coming up with false propositions that we believe are true. So we will again start with the left-hand side and try to produce the right-hand side. So by hypothesis, we assume that this is true, P and not P. By symbolic deduction, since that is a generality and it's an and statement, both parts have to be true if it's true. So I can pull P out of there and insist that it is true. Right? So if 1 is true, then 2 is true. But of course, with disjunctive augmentation or addition, I can combine P by or with any proposition whatsoever. So I do that here. And so clearly, if P is true, then P or Q is true. Right? Again, applying symbolic deduction to this and statement, I can assert the truth of the second component because if this is true, that will have to be true. And so I put it right down there, right, which gives me negative P. But now I have access to another rule of disjunction, which we have not seen, that allows me to reduce a disjunction. If I have a disjunction that I know to be true, and I find out that one of the sides is false, I know necessarily that the other side has to be true because this statement cannot be true with two false parts. So if this is true, and as this says, this is false, Q has to be true. And so I can put that right down there. And so basically the truth of P and not P implies the truth of Q, which stands for any proposition whatsoever, and so this contradiction implies any proposition whatsoever, and that's why we do not allow contradictions in formal logic. This ends the video for today. I hope it has been informative to you. I will consider, and I am considering doing more videos along these lines because I do have a great love of formal logic, and it always bothers me when someone expresses a knowledge of formal logic and they do so in such a way that involves themselves in contradictions and stuff like that. Thank you.